Hello, everyone, and welcome to this latest webinar from Omdia, brought to you by Informatech. My name is Alan Titara, Senior Event Manager for the Omdia webinar team, and I want to thank everyone for joining us. Today's webinar is how to future-proof your 5G transport network. Today, our panel will explore what infrastructure investments will be needed, which tools are available to meet demand and generate revenue, and how operators can benchmark network performance. Our webinar is co-presented by Omdia and our partners Anritsu, Fujitsu Network Communications, and Volta Networks. So before we get started, let me just highlight some of the features that are available for you on our webinar. So the console that you're looking at, it is completely customizable. So this means you can open, close, move, or even resize any of the windows that you have open on your screen and arrange the console to suit your preference. Now, at the bottom of your console are a number of application widgets. Make sure you check out the resource list widget, for this is where you will find additional material about our topic, including the downloadable slide deck from our session, as well as other valuable information, including a special report authored by analyst Richard Webb. You will also see a Twitter widget, which means you can tweet directly from within the console. And today we are using the hashtag 5G Transport Network. We will also have a live Q&A session right after our presentation, so please submit your questions or comments at any time by using that Q&A box that is on the left side of your screen. Please note that this webinar is being recorded and that the on-demand version will be sent out to you within about 24 hours. And if you experience any technical issues, just click on that question mark widget and you will get the answers that you need. So now let me introduce our panel. First leading our discussion is Richard Webb. Richard is Director of Research and Analysis in the Service Provider Technology segment at Omdia. We are also joined by Daniel Gonzalez. Daniel is Business Development Manager at Anritsu. We also have Joseph Masarino. Joe is a Principal Solutions Architect in the Optical Networking Group at Fujitsu Network Communications. And rounding out our panel, we have Hugh Kelly. Hugh is the Vice President of Marketing at Volta Networks. So welcome to our panel. We are honored to have all of you with us today. So now let me turn things over to Richard so we can get started. Richard?
Thanks, Alan. Hello and welcome, everyone. So just to start us off, I'm going to run through a couple of slides to set the scene a little and give some context to the focus of our webinar today. I'm going to start by briefly giving some context around 5G and spend a few minutes focusing on some of the characteristics of 5G radios. So firstly, 5G new radio supports brand new swathes of unused spectrum from very low to very high frequency bands with ultra-wide channels. In existing bands, channels are 5 meg up to 20 megahertz wide, but above 6 gigahertz frequencies, channels can be wider than 100 megahertz, which in turn delivers huge gigabit throughput. There are native forward compatibility mechanisms with 5G new radio frames defined in units of 10 milliseconds and subframes defined in units of 1 millisecond. Within 5G, of course, there's many different use cases, some of which require ultra-low latency. And whilst not all 5G networks require this, 5G is typically more latency sensitive than LTE. So in order to achieve ultra-high data bit rates whilst also supporting ultra-low latency, the industry's agreed to adopt polar coding for the control channel and LDPC low-density parity check for the corresponding data channel. But end-to-end ultra-low latency solutions, which include 5G access, backhaul, private cloud deployments, and the backbone network, of course, are vital. Whether the transport network can coordinate with the RAN to support ultra-low latency is also very important, because latency in the wireless air interface is likely to change dynamically, and that's something operators need to consider and plan for. And speaking of the RAN, 5G architectures can be more flexible and modular than previous generations of mobile networks. So that means transport must also be more flexible as well. And finally, there's support for network slicing. The 5G next-gen core consists of 3 network slicing layers: the service instance layer, the network slice instance layer, and the resource layer. And so it allocates a slice for each particular use case rather than build a dedicated core network, as is currently done in LTE networks. And that's something we'll definitely be returning to in detail later on. So 5G drives transformation of network architecture, as I mentioned in the previous slide. Whilst we will, of course, continue to see the traditional distributed RANs that have formed the basis of 2, 3G and LTE networks, we're going to see more variants as well. For example, centralized RAN. This has been present in LTE. It's an architecture in which the base station is split into two parts, the radio head and the baseband unit. And in 5G, the baseband unit is disaggregated further into control units and distributed units. Then we get vRAN, virtualized RAN, evolving from CRAN, leveraging virtualization of RAN control functions. Just move my slide back. There we go. Jumped a little. So the point being, 5G is very complex. There's more architectural options for operators, there's more traffic, there's more apps, there's more users, all of whom have unique requirements. And as network usage evolves, the network must adapt to accommodate that usage complexity. So it needs more intelligence, it needs more flexibility, as well as more capacity. Then consider this within a multi-vendor environment, which is what you get with the Open RAN movement. The flexibility to integrate and interoperate RAN using solutions from multiple different suppliers. So again, more complexity, more challenges in making the network function as one uniform platform. So hopefully that sets the scene a little bit in terms of some of the challenges that 5G brings, some of the changes it drives. So now let's look at some of those challenges in a little bit more detail, what that means for the network. So I'm going to start with Joe Mosserino from Fujitsu to kick us off, followed by Hugh Kelly from Volta, and then Daniel Gonzalez of Anritsu. So Joe, perhaps you can start us off. What are some of the initial considerations for operators when they're looking at 5G services?
Well, thank you, Richard. Some of those issues are explained here, where 5G services will enable service providers to offer significantly greater service capacities while also lowering the cost per bit, a typical dilemma that service providers have. Legacy services will still need to be maintained for some time after the 5G service availability, and so legacy service support is still required. 5G also offers many new use cases, but how do service providers cost effectively address these new applications when the performance requirements are disparate? Another area is what type of radio do the service provider utilize for their new 5G services? Well, there are two types main radios that are used for 5G new radio services, millimeter wave and sub-6 gigahertz. Millimeter wave are very high frequency radios operating in the 24 gigahertz band and above, and their high frequency range offers very high capacity, as high as 20 gigabits per second service. But however, they cannot go through solid objects like buildings and trees, and therefore an indoor and outdoor approach is required. For the outdoor approach, a densification strategy is required, similar to that used in small cell deployment. Therefore, deployment of these millimeter wave 5G radios will be on street lamps and utility poles and sides of buildings. Sub-6 gigahertz radios use a lower spectrum than millimeter wave, closer to the 4G LTE range, providing greater service capacity than 4G radios, but much lower than the millimeter wave radios. As a result, coverage is similar to 4G and will be deployed on traditional cell towers. So let me pass this over to you at Volta Networks. You?
Thanks, Joe. So if we start to take that new radio and kind of the existing 4G, a few things jump out. First, let's kind of look at the small cell site forum's projections of growth. So you can see small cell sites are expected to grow very dramatically over the existing install base, and in fact will ultimately start displacing some of the 4G. But as was previously mentioned, we're going to see a coexistence of 4G and 5G in these networks in order to drive these services. And really, services are ultimately what this is all about, right? Nobody is installing 5G simply because it's cool. We're bringing 5G to market because there are all sorts of new service opportunities for the mobile network operator. But there are much higher bandwidth requirements, as was noted, and ultimately, this provides a number of challenges around scale, right? If you're seeing this kind of dramatic increase in the number of locations, that is certainly going to have a bearing on things. And I'm taking kind of the perspective of a routing vendor, and so I'm very sensitive to where routers will be placed in this and where the service intelligence ultimately resides. So unlike traditional backhaul, which is more of a layer 2 function, we're now going to see layer 3 moving very, very close to the user equipment out near the cell towers in particular, what are now becoming referred to as cell site gateway routers or disaggregated cell site gateways. And because we're seeing such a massive increase in the number of locations where these are going to go, you're going to see, I would expect, a dramatic reduction in the price point that's required in order to make this economical. And that's certainly the kinds of projects that are out there in the market right now are calling for relatively small devices, but ones that can deliver fairly high bandwidth. Because as was noted earlier, if you're going to see a lot more cell sites that are being able to connect much higher bandwidth services, you're going to see a much greater demand on the front haul portion of the network, right? That connection between the cell site and the central office. And routing is going to become much more important throughout this. So we're going to see that order of magnitude change, which I think has an impact both on CapEx and how service providers approach the OpEx. So let me turn things over now to Daniel from Anritsu.
Thank you, Hugh. So in addition to the bandwidth and latency requirements from the RAN discussed by both Hugh and Joe in the previous slides, you also have to consider when you're future-proofing your 5G transport network, that you must consider how you're going to support the challenging 5G timing and synchronization requirements. So in the 3GPP release 15 and then the upcoming release 16 stage 3, there are minimal cell phase and frequency synchronization requirements documented for both LTE Advanced and for 5G TDD or time division duplexing. At minimum, both the LTE Advanced and 5G TDD sites required to be within 3 microseconds of timing alignment error or TAE, which is relative error between the sites as shown in this picture on to the right. Also, each site has to be within 1.5 microseconds of the timing error from the reference source, or in this case, a timing grandmaster, the TGM, through that edge transport network. So why is this required? So for 5G TDD and LTE Advanced, you're seeing an introduction of new applications such as coordinated multipoint or CONP, increased radio density that was mentioned by Joe, as well as ultra-reliable low latency communication that was mentioned by Hugh. And now this is pushing accurate timing and phase from a nice to have to being an absolute requirement. So the challenge becomes, how do you meet those precise timing, phase, and frequency requirements through an edge transport network? And we'll discuss that in a later section of the presentation. So with that, I'm going to hand it back to Richard for our next discussion topic.
Thanks, Daniel. So a good overview there, I think, of some of the key considerations and challenges in planning the transport network for 5G, scaling it up, also implementing time and synchronization. So now we're going to look at some of the solutions, and I'm going to ask Hugh to start us off this time. So Hugh, over to you.
Thanks, Richard. So there's obviously a lot of work that's being done by a variety of standards bodies and consortia in this. Someone once made the comment, the nice thing about standards is there are so many to choose from. Well, I think here what we're seeing is a set of standards and then models for how to use them. Obviously the relevant standards are things like 3GPP because for a transport standpoint, they're defining the functional splits. IEEE 1914.1, for example, discusses how to implement a front haul transport network. There's obviously eCPRI standards, and these are all interrelated, IEEE radio over Ethernet. But putting these together in a coherent model, one approach has been with the Telecom Infra Project's approach for disaggregating and opening the transport network for the service providers. Their goal is ultimately to have an ecosystem that service providers can pick and choose from. And they've done a tremendous amount of work in kind of defining these different areas. And this is their vision for this. And so from a routing standpoint, they really kind of see two projects. The disaggregated cell site gateway, which is providing the connectivity to the cell towers, as well as then the disaggregated open router, which is a slightly different project designed to address the aggregation and ultimately the core routing functions. Obviously, the bandwidth requirements, just as a starting point, ripple through the whole network, right? The more bandwidth you're putting in at the edge, the more critical then the capacity of the network becomes. And routing is particularly important because you're dealing with a very wide range of different kinds of transport, the traffic that you're trying to move through the network. So some of these drivers, when we start looking at obviously the bandwidth, it's what we've talked about in terms of RAN, but also as we zoom in on that diagram and look at the cell site gateway, typically they're talking about connecting 3 cell sites with 1 gateway, right? And so that can be a large amount of data right there, but also using, pulling in the OLTs, the broadband services, as well as enterprise CPE. And obviously one of the use cases with enhanced mobile broadband is providing connectivity for services like SD-WAN. And that's something that a number of studies have shown that enterprises are incredibly interested in because it's easy to deploy and gives them a lot of flexibility. But ultimately, this whole architectural approach is designed to help reduce cost. One, through commodity hardware. They're using off-the-shelf ASICs and specifying the requirements. The disaggregation of hardware and software. They can choose a hardware platform separate from the software that runs on it. And they're really looking to minimize the vendor lock-in by building an ecosystem of interoperable parts. And a lot of this, ultimately, the goal is to try to, the underlying driver, is that they need to be able to justify this with new revenue. And I think it comes in a couple of ways. Certainly, RAN sharing is something, especially outside of the US, that's getting a lot of interest. And that helps keep the costs down. But also, it's a revenue opportunity for the people that have traditionally owned and operated cell towers. And ultimately, if we're talking about future-proofing the transport network, it needs to be able to accommodate network slicing. That's what's going to allow all these different services to coexist on virtualized pieces of the network on common infrastructure. And that's, I think, critically important. So the transport model that whatever we do needs to be able to get to that point. So I'll turn this back over to Joe.
Well, thank you, Hugh. Well, I'm going to look at several different transport challenges that are occurring. The first is using a new technology that we refer to as a hybrid active-passive. This active hub and passive cell site technology is utilizing smart self-tuning pluggable optics and a wave division multiplexer at each end of the circuit. The self-tuning optics automatically tune to unused wavelengths on the dark fiber transport. So they're automated in such a way that the WDM wavelength is automatically determined by just interconnecting the fiber to them. They also have an in-band channel to assist in remote communications. The cell site end is fully passive, while the hub end utilizes active transponders with integrated performance monitoring and line testing capabilities for OEM functions used over the smart optics in-band communications channel. The hybrid active-passive topology is the best approach for small cell deployments when dedicated dark fiber assets are unavailable. At the cell site, no additional power is needed for transport. The outside plant enclosure containing the WDM is compact and storm resistant. Essentially, the hybrid active-passive transport options is a low cost approach for transport with remote OEM visibility at small cell locations. Let's look at time-sensitive networking. Time-sensitive networking, or TSN, offers packetized transport of cell site traffic for xHaul. It utilizes a series of IEEE 802 capabilities. 802.1cm provides TSN for front haul specifically, consisting of precision time protocol for transport of time-sensitive traffic, including CPRI and eCPRI types of time-sensitive traffic. The preemption function enables the blending of Ethernet traffic with CPRI and eCPRI to ensure their time sensitivity. IEEE 1914.3 describes radio over Ethernet, which is an Ethernet encapsulation of the 4G CPRI traffic. Altogether, these topologies or technologies optimize transport at traditional cell site towers and offer a much lower total cost of ownership than a fully active WDM approach. The mid-haul and backhaul of the 5G network will require dynamic multi-point connectivity. In fact, you had related this during his discussion on the overall 5G network. And this is using essentially layer 3 routing to offer the best options for network slicing capability. A traditional router consists of an integrated control and user plane. While modular, its scalability is limited to a fixed plug-in control card, and visibility is limited to the next router hop within that mesh of routers. To resolve these limitations, the next generation router employs a programmable, disaggregated control and user plane architecture. The control plane is completely independent of the user plane, and in advanced models, it is hosted and executed in the cloud along with the routing engine. Scaling is much more flexible via cloud-based control, and having the routing engine in the cloud gives complete visibility of the entire network, resulting in higher performance for service connections. Cloud-based routing establishes a global service level of connectivity for each service instance and pushes the mapping to the user plane edge switches. In cloud-based routing, every edge switch is capable of dynamically producing hundreds of router instances, each isolated from the other for RAN services. The user plane edge switches provide the common baseline transport infrastructure, and this virtualization of the transport enables multiple isolated topologies used in network slicing within the same baseline infrastructure, eliminating costly network overlays. Let me hand it over to Danny at Enritsu.
Thanks, Joe. And to build on what both Hugh and Joe just discussed, one of the transport solutions mentioned earlier for time-sensitive networking to support network synchronization is Precision Time Protocol, or PTP. In this slide, I'm displaying a simplified high-level diagram of how that timing flows, starting from the Edge Grandmaster, which is on the right-hand side of the slide, through the Edge Transport Network to various cell sites that are on the left-hand side. Now, the Grandmaster clock is responsible for generating the original PTP Ethernet packet derived from a reference source. In this case, it's multiple GNSS or GPS satellites. The packets are distributed through the boundary clocks within the PTP network cloud until they reach the slave clocks, which are located at the sites. Now, in this case, both the time-sensitive network edge transport equipment that was just described by Joe in his previous slides, as well as the disaggregated cell site gateway synchronization requirements that are defined by TIP, which was mentioned by Hugh earlier in this presentation, can support both time and phase synchronization requirements, time, phase, and frequency requirements. So the benefits of this solution is that every site has its own dedicated path, and it maintains both phase and time synchronization from the same reference. Now, let's also discuss, though, that there are also several key factors that you have to take into consideration when you're implementing this packet-based timing and phase synchronization transport, such as precision time protocol. So in this slide, I highlight a few of those considerations which impact that PTP performance over a transport network. And this must be taken into account when you're future-proofing your edge network to meet the 3GPP 5G sync threshold requirements over a transport network. So first, you have to remember that the PTP performance is impacted by timing error. And timing error consists of both dynamic and constant time error. Both types of errors are related to the latency and packet delay variation over your packet network. So some of the issues and concerns that Hugh brought up earlier are also what's going to affect that of their PTP performance. So maintaining that synchronization is directly related to maintaining that latency and PDV. We'll discuss various methods for measuring timing error through your transport network, as well as including how to verify PTP is provisioned correctly and if it meets timing error later on in this presentation. So with that, let me hand it back to Richard to continue.
Okay, thanks very much, Daniel. Before we do move on, just a reminder to all of our audience that we will have Q&A live at the back end of the webinar when we've gone through our slide-based content. So do keep those questions coming. We'll do our best to get through as many of those right at the end of the webinar as possible. Okay, so we've had a look at some of the problems and challenges of 5G. We've had a look at some of the solutions, but in this section, we're going to consider what this looks like from an operator's perspective. How do they implement these solutions? What the kind of roadmap looks like for them? And again, depending on what type of 5G they're trying to put in place. So we're going to try and put some context to that and share it from an operator's perspective. I'm going to start off by asking Joe to tell us a little bit more about some of the various deployment applications, please. Joe, over to you.
Thank you, Richard. For small cell deployments, given the power and footprint challenges at the cell site, that cell site being a street lamp, a utility pole, the side of a building, the hybrid active passive solution is optimum in terms of providing a cost-effective solution that's right-sized for the cell site, while supporting a level of remote visibility for performance monitoring and proactive maintenance. Here in this illustration, we have the hybrid active passive configuration with smart self-tuning optics in linear or point-to-multipoint topologies. The cell site transport end is fully passive and does not require any power. The footprint for the outside plant WDM and its enclosure is slightly larger than, say, a tall coffee mug, and thus saving on footprint where it is at a premium. Optimal macro site front haul uses time-sensitive networking switch aggregation units, or TSN muxes, in a point-to-multipoint type of topology as shown here. It's used to transport 4G CPRI from remote radio heads, 5G eCPRI from radio units, and Ethernet services from a macro cell site to a centralized hub over 100 gigabit per second links. The TSN MUX uses precision time protocol, as mentioned by Danny at Inritsu, enabling high hub location to operate as a boundary clock, transporting in-band timing and synchronization to remote cell sites. Having this remote timing capability eliminates having to have GPS receivers at all the cell sites. And using a TSN switch aggregator lowers the total cost of ownership as compared to an active WDM through lower cost, smaller footprint, and automated provisioning. Virtual RANs offer the service provider the greatest flexibility and cost efficiencies via a common baseline infrastructure with multiple microservices. This is accomplished using a mix of software-defined networking, orchestration of the RAN, transport of control, core control planes, and networking functions virtualization, altogether providing an end-to-end network slicing capability. In this deployment, application of the virtual RAN mid-haul and backhaul segments I show, where there is a baseline network infrastructure consisting of commercial off-the-shelf servers or COTS used to abstract the RAN elements, and the disaggregated edge switch with cloud-based routing, providing the dynamic transport and connectivity for the RAN elements. The network orchestrator coordinates between the RAN, edge transport, and core elements. As network slices are established via a distribution unit or a DU asset and multiple central user plane or CU-U terminations, the cloud-based routing and edge transport establishes router instances to support these individual services, providing the transport QoS guarantees. The first network slice, as shown here as an enhanced mobile broadband service, and the second network slice, as shown using ultra-reliable, low-latency connectivity. Both are on the same baseline infrastructure, but isolated and sliced at the virtual distribution unit, or DU. The advantages of this virtualized infrastructure are zero-touch deployment with automation, peak utilization of assets minimizing or eliminating idle capacity, and OpEx savings for virtual infrastructure using unified user plane hardware requiring fewer site visits and minimizing the spares pool of assets. Let me hand it over to you, Kelly, at both the networks. You?
Thanks, Joe. Yeah, so let's drill into that a little bit deeper. Joe was kind of talking about kind of how the whole network can be split up in different ways. Ultimately, that network needs to be able to accommodate a range of new services, right? We're talking about future-proofing, and in the future, network slicing is expected to be very important. The standards really define three broad categories of services. Enhanced mobile broadband, that high gigabit connectivity rate. I gave the example that even today, enterprises are using mobile connections in order to be able to provision SD-WAN at branches. That will only expand and put a lot of bandwidth onto the network. Ultra-reliable low latency communications. So think of those as things like connected cars. Right? Not high bandwidth, but it needs to be incredibly reliable. So when we talk about latency requirements for applications, that's one of those. And that will obviously have a ripple effect on how everything is architected, where all these different pieces are, because latency budgets matter a great deal. And the final category is the massive machine-to-machine communications. Right, so think of that as kind of the IoT world, smart cities, sensors in all these different things that help enable all of these new kinds of capabilities. But the reality is that those all have to be able to run over the same physical infrastructure. And so the whole idea of network slicing is to be able to run virtual layers on top of that common infrastructure. Yet there are major differences in the bandwidth requirements, the latency budgets, how you approach QoS, and obviously service level agreements, right? If I'm going to be charging differently for different services, I need to be able to show my customers that I'm actually delivering what it is that they're paying for, right? So when we start talking about all these different services, when we're talking about the RU, the CU, and the DU, and the different ways of implementing functional splits in the network, a lot of that is driven by virtualization, right? The DU goes from being a physical device to a virtual network function, or VNF, that's running as a piece of software on commodity hardware. That's one of the options. And the CU can be split up. And the whole idea there is to be able to do a little bit more centralization to gain economies of scale, better utilization of the network. But with network slicing applications, you're going to need to be prepared to manage a lot of different kinds of traffic, right? Here we're just talking about the different kinds of user traffic. There's control plane traffic and all sorts of other things that need to be accommodated in that. Now, obviously, these all deal with differences in terms of the different QoS functions. So our basic approach is, as we see is important, is virtualization needs to be extended out to the cell site gateway so that it can provide different management domains, different routing protocol stacks if necessary, as well as being able to have different cross functions. And routing is going to be important at this point because given the complexity of the traffic and the different latency requirements in particular, traffic engineering using a technology like segment routing is going to be very, very important. And that pushes that service intelligence all the way out to the edge of the network. So we're now going to see a lot more intelligence embedded in the network that's really only going to be made possible through virtualization. So let me pass things over to Danny from Enritsu.
Thank you, Hugh. And I believe you said it best when you posed the question, what are we future-proofing the 5G network for? And in this section, as we're talking about deploying new network transport devices to support both virtualization, and you're seeing the introduction of cell site gateways to future-proof your 5G network, taking the timing and synchronization into consideration, you have to identify what your timing error budget is for each portion of that network. So follow with me here as we're starting from the bottom of the slide where we're introducing the Edge Grandmaster is receiving that primary reference clock or the PRTC. And then that timing error is introduced right there starting with the Edge Grandmaster. And then it gradually builds as you're going through the various types of devices. Now you'll notice that I identify a couple different classes here. And again, this is based on the network elements. There's a class A type that introduces a slightly more timing error than that of a class B type. And then the class type C introduces even less timing error than that of a class B. So this is an important factor when you're determining how many network devices that you can actually install to support your distribution of your PTP or synchronization timing throughout your edge network. In addition to the timing error from the network devices, you must also take into consideration the timing error introduced from the latency and link asymmetries. So you'll see that noted in green in these sections. Altogether, and again, per the standard, the goal is to keep that timing error under 1.1 microseconds over the transport network because the total of 1.5 microseconds also includes over the air. So you have to take out the 400 nanoseconds over the air in order to complete the to add that to the 1.1 microseconds so you have your total. So where does that leave us? Well, as we've seen in deployments, in initial providers rollout of 5G edge transport networks, they're updating both their CRAN and their edge networks to support these new applications along with packet-based timing and synchronization to meet those measurement timing error and protocol provisionings up to and including the DU and RU. For most carriers in the US, PTP or NTP served as a timing backup or a secondary from the switch or the backhaul in the event that timing was lost or in holdover when GPS wasn't available. However, now that we're moving forward as PTP transitions into as a primary phase in timing synchronization tool at the edge and again through the CRAN and ultimately to the site, carriers find themselves measuring that timing error in protocol performance after provisioning and turnup, as well as for troubleshooting once they deploy that 5G service. So again, the purpose of this is to determine if there's synchronization errors reported on the RAN and exactly at what part, based on that different budget, where is that total error coming from? So with that, I'll hand it back over to Richard.
Thanks very much, Daniel. So now, before we go into our conclusions and live Q&A, we're going to take a moment to hear about the solutions of the vendors represented by our speakers here today. So going in alphabetical order by company, we're going to start with Anritsu, followed by Fujitsu, and then Volta Network. So it's actually back to you, Daniel. So please go ahead.
Thank you, Richard. So for those of you that are not familiar, the Anritsu Test and Measurements offers the MT1000 Network Master Pro. And what this is being used in current 5G deployments, it's a portable handheld transport optical tester that's used by carriers, contractors, and engineers that are performing both existing 4G LTE measurements as well as the new 5G measurements in both field and lab applications. So in this slide, we're just showing the capabilities of performing that PTP measurement, which includes the timing, error, and protocol verification based on various telecom profiles, be it G.8275.1 or .2. The tester also has a built-in OTDR. It supports both eCPRI and the 1914.3 radio over Ethernet traffic verification for xHaul, and the latency, throughput, and QoS measurements that were discussed in previous slides by both Hugh and Joe. And it allows the MT1000 to be a complete all-in-one tester for 5G transport testing. With that, I'll hand it over to Joe to discuss Fujitsu.
Well, thank you, Danny. Fujitsu has a set of products that have been developing the most transport networks within some of the largest service providers networks in the world. We have a branding that we refer to as our Smart xHaul solution set, and this consists of front haul, mid haul, and back haul solutions that are modular, disaggregated, and are right-sized for the application for transporting 4G CPRI, 5G eCPRI, and Ethernet transport for coexistence and end-to-end transport. Using WDM and Ethernet technologies, along with TSN switch and aggregation and cloud-based routing, these SDN control and management systems are fully automated to provide the different types of networks over a single baseline infrastructure for the most flexible and scalable operation for 5G services. We also have a services group that provide turnkey services in terms of design, supply chain, rack cabinet integration, deployment, and then post-management of the overall network end-to-end within the overall service. These capabilities provide that full 5G service capability for multiple types of operations as well as different types of topologies. Let me hand it over to Kelly of Volta Networks.
Thanks, Joe. So Volta is a routing vendor. We have a platform that fully disaggregates the router and works with open networking concepts. So we work with, for example, white box switches, where we put an agent on the box. But rather, unlike a network operating system, the bulk of the control plane runs in the cloud, right? So we can run on any public, private, or even hybrid cloud. And because the control plane is very processor intensive and memory intensive, the cloud turns out to be a great way to scale that cost effectively, which then allows us to be able to run multiple separate instances of the control plane, each one its own management domain, running its own set of protocol stacks with its own policies. And those can then be associated with resources on the open network device. So whether they're physical or virtual ports, doesn't make any difference. So we can scale that up into the hundreds of virtual routers. We call the cloud components the vCluster. So it's a turnkey system that can deliver all of this functionality. And because everything is centralized in the cloud, we give our customer a lot of visibility into all of the activities that's happening with routing. And it also provides a way to be able to use APIs into the cloud to be able to do management and orchestration integration. We have a number of different Yang service models compatible with NetConf so that we can help drive carrier scale automation to help make the high scalability, the complex service requirements, and the need for virtualization a reality inside carrier networks. And with that, I'll turn it back over to Richard.
Great, thank you very much, Danny, Joe, and Hugh. So we're just going to wrap up quickly with a few takeaway points before we head into the live Q&A. So at the top of the webinar, I outlined some of the characteristics of 5G new radio and new 5G architectures and how they bring new challenges in terms of planning, deployment, performance, operations, and then we heard from our speakers about some of the new characteristics of RAN architecture and the challenges to xHaul, particularly in terms of the radios. We talked about the spectrum and again, those architectures. And then Joe, Hugh, and Daniel outlined the service challenges, increasing capacity whilst lowering costs, supporting legacy, whilst evolving 5G performance requirements for enhanced mobile broadband, ultra-reliable, low-latency communications, and so on. And then we heard more about the challenges that are brought by scaling up the network, particularly when you've got densification of the network and small cell type deployments. And then Daniel from also talked about the timing and sync challenges. And that's particularly relevant because we're talking about TDD spectrum here, and that brings challenges that's different to FDD. And then our speakers looked at xHaul and various models, particularly the model for disaggregated and open transport networks, and reviewed some of the technology solutions such as active passive WDM and time-sensitive networking. We also covered the role of virtual routing in network slicing and what that means to operators in terms of revenue opportunities, but also getting the transport network arranged to accommodate that. And then finally, they outlined network-based timing and sync and the importance of time budgeting across the transport network. Okay, so hopefully we have lots of questions lined up. Yes, we do. So we're going to go into our Q&A part of the webinar now. So thank you for sending those questions through to us. So the first question is related to small cells and front haul connectivity. And the question is this: if small cell front haul connectivity does not need TSN, can the macro cell front haul connectivity non-TSN? Anyone want to take that one first? Maybe Joe or Hugh?
Sure, I can address that. So in small cell front haul connectivity, if it is front haul, it could be front haul, it could be back haul for the small cell deployment. Synchronization and timing is still absolutely required. It may not use a time-sensitive networking multiplexer aggregator to provide that transport, but timing and synchronization is still absolutely required. It's typically passed in using WDM type systems, as I showed with the hybrid active passive, for example. The timing and synchronization is passed through in-band on CIPRI channels, eCIPRI channels to provide that capability.
Thanks, Joe. Anyone else want to jump in on that one, or should we move on to the next question? Hugh, anything to add?
No, I think Joe makes a number of good points. One thing I'll just add is there is no one size fits all, right? We're going to see a mix of a lot of different things. It's how you design the transport network to be flexible to meet all the different use cases that you as a mobile network operator need to accommodate.
Yeah, and this is Danny. I would agree with both Joe and Hugh, and I liked how Hugh mentioned that there is no one size fits all. We've seen a combination of everything where, depending on the site location, line of sky, or visibility to the sky, there's a combination of GPS still being the primary use. But with that, having either PTP or a time-sensitive, like a .2 profile, partial timing support to the site, either as a redundant or as a backup. It really depends on the deployment aspect, where the site's going, what kind of options are available, and then what's feasible as far as transport. Because it may be a combination of fiber, it could be a microwave link. So it really varies by case to case.
Okay, thanks, gents. Okay, we've got another question, and we're sticking with TSN, this one. Is the uplink of TSN limited to 100 gig? And this, is a question kind of taking into consideration the potential for site sharing, including more than one operator in the site. Would it be limited in that case? Any comments on that?
I could comment on that. In fact, the TSN MUXs aggregators typically have up to 400 gigabit links for traffic, especially with the eCPRI traffic. eCPRI typically will operate anywhere from 10 gigabits per second per channel to 25 gigabits per second per channel, and typically there'll be, for a 3-sector type of configuration, 3 channels of those. So just the 3-sector 5G area could utilize most of one of the 100 gigabit per second types of links. But there are multiple links. These are also stackable units. So as more that's needed, stacking these TSN MUXs on one another to provide scalability is also an option for use, especially since the front haul access for them is all point-to-point to a specific location.
Yep, thanks, Joe. Any further comments? Okay, let's move on to the next question in that case. This is one I think I'm going to hand to you first of all. This is a question about virtual routers, which you were talking about at some length. Do you see virtual routers as replacing the infrastructure routers from some of the traditional legacy vendors or some of the large integrated vendors that have kind of, established themselves as router providers in the early days of the internet? I think we know the folks that we might be talking about. Or do you see a need for infrastructure routing with some of the edge functionality moved to virtual routing? How do you see it?
Yeah, so it's an interesting question. One of the things that I think is interesting about the 5G new service edge is it is essentially a greenfield build-out. So it is allowing operators to be able to rethink how they do things. I'll point to TIP again as an example. They're committed to building an ecosystem of interoperable vendors, but I think they feel very strongly that disaggregation is important. We certainly think virtual routing is incredibly important. And I want to point out there's really kind of 2 flavors of virtual routing. You certainly see things in data centers where routers can be run as a virtual machine. That's running on an x86 data plane. The only way that you can meet the cost goals of something like a disaggregated cell site gateway is to be able to use an ASIC, like a lot of them call out like a Broadcom Qumran. That's a whole different flavor of virtualization, right? So there's kind of 2 different flavors. So even though Cisco and Juniper have a robust service offering in the area of VNFs, that doesn't necessarily translate to virtual routing. So we see it ultimately being interoperable. And that's one of the great thing about all the standards is it's pretty easy to implement the routing protocols in such a way that it can coexist with all the legacy infrastructure. So this can be an evolutionary approach in this greenfield build-out, yet it can still meet the service requirements long-term, and again, getting back to our topic of future-proofing the 5G transport network.
Okay, thanks, Hugh. Any further comments? Joe wanted to chip in on that, or Daniel?
I think you handled it well. Thank you.
I agree. Okay, so I've got a question that I think actually I'm going to turn over to Danny first of all. It's regarding millimeter wave 5G deployments, and as we heard, I think from Joe at the top end, millimeter wave deployments are going to result in the explosion of cell site numbers. The question is, does PTP become the primary source of synchronization in this particular scenario? Any other sort of sync sources that could potentially come into play there?
Yeah, and that's a good question, and we've actually fielded this from several different vendors that have asked similar questions to this. And what you're really looking at, especially with millimeter wave, and as you mentioned, Joe pointed this out earlier about, the limitations as not being able to go through walls. It's easily blocked depending on the environment. You're looking at a high density of millimeter wave radios in order to have the full coverage in a specific area, to be able to provide the bandwidth that they want as far as over-the-air bandwidth and supporting applications, as I mentioned, like coordinated multi-point. You're really looking at the sheer density, which is, I think, what the the attendee, when he submitted the question, they're absolutely right that you're really looking at a density issue. So the reason why PTP, and not just PTP, but a packet-based, a network-based timing solution, and there are a couple. PTP is just one because it supports both frequency and phase synchronization capabilities. That's what we're seeing the most common, is that you're able to distribute that timing through your transport network to a high number of sites in a concentrated area using that same reference. The challenge that you'd have in the case of like millimeter wave, especially when you're looking at street level deployment or urban canyons, as we call it, is clear line of sky if you're trying to use GPS. You'll have everything from difficulties trying to maintain the GPS accuracy. You also have the cost associated with it. So in the case of a packet-based transport like PTP, where you're investing in the transport network, but you're using the strength of the transport to deploy that timing, you're saving a significant cost versus having to deploy GPS at every small cell that has to have synchronization. So that's one of the primary drivers behind the reason for PTP. So again, it has to do with both the phase as well as frequency synchronization. It has to do with the cost of being able to deploy less GPS, as well as the accuracy of being able to provide that timing through transport, whereas losing timing over GPS.
Okay, thanks very much, Daniel. Very full answer there, much appreciated. I think we've got time for one more question, which is as follows. Today, 5G RUs and BBUs, the radio unit, baseband unit, are co-located at the cell site with backhaul connectivity. But going forward, when we talked about network architecture evolution, are we going to see those sites transition to be disaggregated and, with part of the cell split off and then backhaul links be transformed into front haul links? So yes, we're going to see front haul potentially in certain deployment scenarios, but are we actually going to see those traditional distributed RANs get converted to centralized RANs or even virtualized RANs? Anyone want to comment on that? Maybe that might be one for Joe to start us off with.
Great. Yeah, that is a great question. I don't foresee a lot of changes to the existing network in place, the 4G network being mostly distributed today. There are, in certain very, very high density areas, a centralized RAN type of topology, but I don't see that really changing as 5G rolls out, because 5G really offers just so many more times the amount of bandwidth capacity than 4G, and deploying 5G in such a way as either distributed or in a centralized RAN still offers many times more amount of bandwidth capacity that can be achieved with 4G. I don't see a lot of change happening to the legacy network, other than there might be some consolidation, and in that consolidation of migrating over to the addition of the 5G network, there could be gateway units that are deployed that will do translation of the 4G CPRI signals to eCPRI, and consolidation of the 4G network into a virtual baseband unit that can essentially integrate the 4G and 5G. Probably we'll see that type of operation again in these dense urban areas where really high demand exists.
Okay, thanks very much, Joe. Sadly, folks, we are at the top of the hour, so we're going to have to draw a line under the Q&A right there. But thank you very much for your questions. We'll do our best to follow up offline in the days and weeks that follow. So thank you very much to Joe, to Hugh, and to Daniel. I'm going to hand us back over to our moderator, Alan Tatara. Alan.
Thank you, Richard. And as you indicated, we did receive a very large number of questions, so our panel will be following up with all of you via email in the days forthcoming. I also want to thank Richard for leading our discussion today, and also my thanks to Daniel, Joe, and Hugh for being a part of our panel. An archived version of this webinar will be made available shortly, so feel free to come back, view this session again, or even share it with your colleagues. You're also going to see a survey pop up at the conclusion of this webinar. Please take a few moments to fill that out, and also please continue to follow us on Twitter and LinkedIn for information on future webinars from Omdia, brought to you by Informatech. So again, thank you for joining us, and have a great rest of your day.